So for chapter 18.6, we're going to go over the division of radicals and how to rationalize a problem. So the concepts are how to simplify a radical, how to divide radicals, and how to rationalize the denominator if we have one term versus two terms. So the first concept here is the simplified form of a radical. So we're just looking at these three criteria here. And these criteria is the same ones from the previous notes. It's just rewritten here just so you have it again. So remember, we know that a radical is simplified if, let me go and highlight, no factor raised to a power greater than or equal to the index. So our power, or in other words, our exponent cannot be greater than that index. The radicand does not contain a fraction. And then lastly, there are no radicals in the denominator. So again, we know that a radical is in simplified form if it meets these three criteria. We're going to be using these concepts when we look at concept 2, division property of radicals. So the division property of radicals states that if we have two radicals, so in this case, radical A and radical B, and we divide them, that's the same as giving the radical to each part. Okay, same thing that we did before. So if we have a radical, so like a square root over a fraction, we can give that square root to the numerator and the denominator. Okay. And then this b cannot equal 0. It's just telling us that in our denominator, we cannot have a 0, or our answer is considered what? If we have a 0 in the denominator, undefined. So that's all this part is saying right here, that b cannot equal 0. So let's go ahead and look at some examples. Example 1, we have the square root of a to the 6th over b to the 4th. So in order to simplify this, remember the two ways I showed you. We could either write the a 6 times, okay, and write the b 6 times and find our pairs. So let's go ahead and do that method first. So this can be rewritten as the square root of a to the 6th over the square root of b to the 4th. So that's using that property of division that says if we are dividing a fraction, we can give that radical to the numerator and the denominator. Okay. We could rewrite this as the square root of a 6 times. So 1, 2, 3, 4, 5, 6. Over the square root of b 4 times. Since we are dealing with the radical square root, that means we're going to be circling pairs of what? 2. Okay, so I have a pair of 2 here for the a's, another pair of 2, and a third pair of 2. How many pairs of 2 do I have for the b's? 2. Do I have any pairs that are left over? Any additional a's or b's?
No.
No. So that means I'm going to have no radicals left. I'm just going to take out one pair from each one. So since I had 3 pairs of the a's, this is going to become a to the 3rd and and the bottom's going to become b squared. This is our answer. So all we're doing is we are simplifying these radicals. Any questions on how I did 1? Okay. What if there were things that did not have pairs? So for example, what if there was an additional a here that did not have a pair? Where would that a go? Under a radical, so our answer would include the square root of a. Okay. So if we have an additional one that does not have a pair, then we still have that square root in our answer. Okay, let's go ahead and look at number 2. Okay. Number 2, we have the cube root. That cube root can be separated into how many radicals? Because how many terms are under that cube root? 3. So we could give that cube root to the 81. We can give the cube root to the y to the 5th. And we can get the cube root to x cubed. So all I'm doing is giving each of these terms their own radical. Makes it easier to simplify. How would we simplify the cube root of 81? We would use what? The prime tree. So 81. And then we start doing the prime factorization off of 81. So we first check 2. Can 2 go in 81? No? What about 3? Yes, so 3 goes in 27 times. What goes into 27? 3. That goes in 9 times. And what 2 prime numbers go into 9? 3 and 3. So since this is the cube root, we are going to be circling pairs of 3. So we have one pair of 3 and then a 3 that does not have a pair. So how could I rewrite that?
3 cube root of 3.
Good. So 3 cube root of 3. So I had 1 pairs of 3, so that came out. And then I had a 3 that was left over, so that has to stay under the cube root. Okay, so now we're done with the 81. Now let's look at the cube root of y to the 5th. So we could think of it 2 ways. We could write that y 5 times and circle pairs of 3, or we could see how many times can 3 go into 5. How many times can 3 go into 5? Once. And if it goes in 1 time, how many is left over? 2. So that means we would take out a y, because it can only go in once, right? And then we're left with the cube root of y squared, because we said there was 2 left over. And you could get this same thing if you did the y 5 times. So if we did y 5 times and did a pair of 3, notice we took out 1 of those y's and we had 2 left on the inside. So 2 different thought processes to get the same answer. Okay. What about that denominator there, the cube root of x cubed? We have matching power and indexes, so that means what? It's going to cancel, and we're going to be left with x. Okay. So before we say this is our final answer, Let's go ahead and combine our numerator. Okay, so in our numerator, we have two terms on the outside of the radicals. What are those two terms? The 3 and the y. Those are on the outside. What is left on the inside of both radicals? 3y squared all over x. That's our answer. So just like we could separate them, we can combine them back. Okay. This would be the answer I'm looking for because this is the most simplified. You'd get points for this answer, just not the full points. Okay, so any questions on 2? Any questions on 2? Okay, let's go ahead and look at number 3. Notice on number 3, our radicals are already separated for our numerator and for our denominator. So just like we could take the rule and say, if we have a fraction, we could write it as 2 separate radicals. We could do the opposite and write this as 1 radical. So this could be written as the 4th root of 8p to the 7th over p to the 3rd. So in this case, I'm not separating them. I put them into 1 radical. And I'm only able to do that because both the indexes on the numerator and the denominator are what? Oops. The same. If they were different, would I be able to do this? No, they would have to stay separated. So since they're both the 4th root. Okay? The reason I'm doing this is because I could use the properties of exponents and I can simplify p to the 7th divided by p to the 3rd. What would that simplify to? P to the 4th. Because remember, if we are dividing exponents, that's the same as subtracting them. So 7 minus 3 is 4. So this becomes the 4th root of 8p to the 4th. Now we could go back and we could separate this into 2 radicals. We could have one with just the 4th root of 8 and then one with the 4th root of p to the 4th. Okay. So for the 4th root of 8, we're going to have to do that prime factor tree off of 8. And when we do that, we start with what prime number? 2, and we get 4. And then off of 4, we get 2 and 2. Since this is the 4th root, we have to have pairs of how many? 4. Can we make a pair of 4? No, so what does that tell you about the 4th root of 8?
That's already simplified.
It's already simplified. We can't simplify further. Can't make pair of 4. So it's already simplified. Okay. What about the 4th root of p to the 4th? What happens to those 4s? 4th root p to the 4th. They cancel, right? If our index and the power are the same, they cancel. So that means our answer is going to be p 4th root of 8. Anytime you have a radical, your radical is going to be at the end. The only reason we do that is because if you wrote 4th root of 8p, sometime there can be some confusion on whether or not that p is under the radical or outside the radical. So we just place the p in the front. Okay. Any questions about this division property?
When you get 8p to the 4th and the index and the exponent are the same, you can't cross those out over there?
For which part?
Right after the highlighted part. The green highlight.
Oh, yes, right here.
Yes.
Yes, you could go ahead and say, okay, these cancel, but you just have to remember you still have to take the 4th root of the number. So I wouldn't cancel it from that step because then you might make the mistake of just writing the answer 8p, which would be wrong. Okay. Good question. Okay, now looking at concept 3, we're looking at how to rationalize the denominator. And all that means is how to remove the radical from the denominator. So how to remove. So first, before we learn how to remove them, we're going to look at a couple concepts here. So 4, 5, and 6. And we're going to see if you understand these properties. Okay. So on number 4, it says the square root of a times the square root of something, it's a mystery, we're trying to figure that out, is equal to the square root of a squared, which is a. What would have to be right here where this question mark is to make this statement true? It would have to be a. This would have to be the square root of a. Because we know with the properties, square root of a times the square root of a is the same as the square root of a squared. We can multiply whatever is inside the radicals. Okay. So that's all for number 4, just talking about that concept. For number 5, we have the cube root of y times the cube root of something is equal to the cube root of y cubed. What would have to be right here in order to have that y cubed as our answer? Y squared. So this would have to be the cube root of y squared. Because cube root of y times the cube root of y squared means we add those exponents on the y's and we get the cube root of y cubed, which cancels out to y. Again, we're just looking at these properties here. Okay. On number 6, we have the 4th root of 2, z to the 3rd, times the 4th root of our mystery number, is equal to the 4th root of 2 to the 4th, z to the 4th. What is missing here to make this statement true? 2 cubed z. So we have 1, 2, and we want 2 to the 4th. So we are missing the 4th root of 2 cubed. We have z cubed, but we want z to the 4th. So that means we are missing 1z. Okay. We need to understand these properties of radicals and these properties of exponents in order to be able to rationalize a denominator. Okay. Any questions on those properties? Okay. Now let's look at our first example to rationalize a denominator. We have number 7, 5 over the cube root of a. Okay. So if we have any radicals in the denominator, in order to get rid of that radical, we are going to have to multiply the top and bottom by whatever radical will cancel out the bottom. So in order to cancel out the cube root of a, we would need a cube root of a what? Okay, so in order for this to cancel out, what would we have to multiply it by to get the cube root of a cubed? That's what we're trying to find.
Oh, a squared.
A squared. So the cube root of a squared. That's what we're multiplying the top and bottom by. Okay. So I have 5 cube root of a times cube root of a squared, cube root of a squared. Okay. We know on the bottom that is going to give us the cube root of a cubed. What is that going to give us on the top? Is that 5 going to stay on the outside, or is it going to go on the inside?
Outside.
Stays on the outside. So this is 5 cube root of a squared. Okay. What can we do to the bottom now to get rid of that radical?
Cancel the exponent and the root.
We have both the exponent and the index are the same, so we cancel them out. So we are just left with a. So we have 5 cube root of a squared over a. That's our answer. Okay, so the only thing that we're trying to do here is make sure we do not have a radical in the denominator. Does not matter if we have one in the numerator. Okay. Looking at number 8. Before we try to solve this, we need to use that division property of radicals and do what to this square root? So right now we have the square root over both of them. We want the square root over each one separately. So we have the square root of y to the 5th, square root of 7. Okay. So in order to cancel out that radical on the bottom, the 7 needs to have what exponent? In order for them to cancel out, remember the index has to match the power, a 2. So in order to have that 7 squared, we would have to multiply the top and bottom by the square root of, remember we're looking at this, we have the square root of 7 times what gives us the square root of 7 squared, because these will cancel. Square root of 7. So I'm going to multiply the top and the bottom by the square root of 7. Okay. This is going to become square root of y to the 5th, square root of 7, all over 7. Good, because remember, this part right here, when we multiply them together, gives us the square root of 7 squared, which cancels the index and the power and leaves us with 7. So just think when you are multiplying the two square roots together, your answer is whatever is in the inside. And we just write one of them. Okay. Can we simplify this further? Yes, we can simplify the y's further. So looking at the square root of y to the 5th, how many times can 2 go into 5? Twice. So that means we have y squared. And how many y's are left over if 2 goes into 5 twice? 1 y. So just a y. And then the square root of 7 over 7. What can I do with those square roots on the top? Put them together. So this is y squared times the square root of 7y all over 7. That's our answer. Again, this is just a note off to the side. Okay. Any questions on how I got that answer? Number 9. So on number 9, we have to figure out what we need to multiply the top and bottom by in order for that cube root to cancel on the bottom. So in order for it to cancel, that means we need to have, so we have the cube root of 25s. We need to multiply it by something that's going to give us the cube root of 25 cubed s cubed. So we can cancel out those cube roots. What is that going to be? It's going to be the cube root of 25, how many exponents? Squared, and then s squared. Okay, so I have 15 over the cube root of 25s times 3 cube root of 25 squared s squared over the cube root of 25 squared s squared. Right away, we know that the bottom is going to be what?
25s.
Good, 25s, because it's going to cancel out. Okay. And the top, for now, we're just going to write that 15 on the outside with the cube root of 25 squared s squared. Okay. So that means all we have left to do is just simplify that radical on the top. Okay. So we have 25 squared, and we need to take the cube root of it. So what's 25 squared? Put it in your calculator. 625, okay. Okay, go ahead and on your calculator, because we don't want to do the prime factor tree for that. That would take a while. I mean, we could. But on your calculator, go ahead and do the cube root of 625 and tell me what it gives you. And see if it will leave it in radical form for you. Does it leave it in radical form, or does it change it to a decimal? The decimal.
Not 100%, but you're right.
Okay, I'm just curious to see if the calculator would give it to you already in the form. If it gives you the decimal, then we will do the prime factor tree. The first prime number that goes into 625 is 5. And 5 goes in 625 divided by 5, 125. And then 5 goes into 125 25 times. 5 goes into 25 5 times. So since we're taking the cube root, how many 5s are we going to pair up? 3, because it's the cube root. Meaning this simplifies to, that 15 still there. So 15 times 5, cube root of 5. And are we able to take the cube root of s squared? No, so I'm just going to leave that x squared there. Okay, all over 25s. Okay, if we multiply 15 times 5, we get 75. And can we simplify 75 divided by 25?
Yes.
And what does that simplify to? 3. 3 over 1. So that means the only thing we have left on the bottom is what? 1 what? S. So we have 3 cube roots of 3 5s squared over s. That's our answer. So I guess instead of using your calculator on this part, because I thought it would give you that radical already, just go ahead and use that prime factor tree. On the test, you're not going to have any numbers this large. When you do your prime factor tree, it's just going to be, take a couple steps. Okay, so that is how to simplify a radical if we have one of them. So if we only had one of them in the denominator. Now, the next part is if we have 2 terms in the denominator. So notice on number 10, we don't just have the square root of 6, we have 2 plus the square root of 6. Okay? In order to rationalize the denominator with 2 terms, we are going to have to use the conjugate. So let me go ahead and write that out. So the conjugate, conjugate is if we have, for example, the term a plus the square root of b, the conjugate would just be the opposite sign. So it would be a minus the square root of b. You would multiply these two together, and you would get a squared minus b. So if we're looking at our terms, 2 plus the square root of 6, what is a and what is b?
B is on top and A is on bottom.
So we're only looking at the denominator here. Only the denominator. Because notice how this, a plus the square root of b, looks like this. 2 plus the square root of 6.
So 2 is A and B is 6.
Correct. So this is a and b. So in order to solve this, we need to multiply the top and the bottom by the opposite sign. So instead of 2 plus, this is going to be 2 minus the square root of 6. Top and bottom. For the bottom, we just use that conjugate formula And we know on the bottom, we are going to have a squared minus b. So we said a is 2. 2 squared is 4 minus b, which is 6. So we're going to leave that as is for now. So 4 minus 6. On the top, what are we going to have to do with that negative 2? Distribute. So what's negative 2 times 2? Negative 4. And what's negative 2 times negative square root of 6? Can we multiply the 2 and 6 together? Yes or no? Are they both radicals? No, so that means we can't multiply them together. So that 2 is going to go on the outside, and that square root of 6 stays on the inside. And the reason that it's positive is because we did a negative times a negative. Okay. Now we simplify. So we have this 4 minus 6 on the bottom, and that becomes what? Negative 2. So we have negative 4 plus 2 square roots of 6 over negative 2. Okay. Looking at the numerator, can we take out a GCF between negative 4 plus 2 square roots of 6?
Yes.
What's the GCF we could take out?
It's either 2 or negative 2. I don't know which would be more beneficial.
Okay, so that's a good point. It could be 2 or negative 2. We want to see if we can cancel out that denominator completely. So what would we take out?
Negative.
Negative 2. So if we take out a negative 2, we would be left with 2 minus the square root of 6 all over negative 2. Which means that these negative 2's cancel, and I'm left with what as my answer? 2 minus the square root of 6. So remember here, we're not solving anything, we are simplifying. We are simplifying as much as we could get. Okay, so we're just going to keep this note of the conjugate off to the side, and we're going to use it for the rest of these problems. So remember, the conjugate is just the opposite sign of that denominator. So looking at number 11, what's the conjugate of the denominator? Correct. So we're going to multiply both sides by the square root of x plus 7. But what do we notice about the numerator in this problem? Does it have one term or two? 2. So that means instead of using the distributive property, we're going to have to use what? Foil. Okay. So let's go ahead and first foil the top, and then we'll simplify the bottom. So foiling the top, we have 4 times the square root of x. So it's just 4 square roots of x. 4 times 7. Oops. 28. And then we have the square root of x times the square root of x, which simplifies to just x, because the square roots cancel. And then the square root of x times 7, which is 7 square roots of x. Looking at the denominator, notice that our a and b values are mixed up. we know that our b value is always the value under the square root. So in this case, our b value is what? Looking at the denominator. X, that's our b value, which means our a value is the 7. So if we look back up at the formula here, it says our answer is a squared minus b. So what's 7 squared? 49 minus b, which means
Minus X.
minus x. Okay.
So does it always have to be that formula then? Like, because if you foiled that out just as it was, wouldn't it be X minus 49?
Yes, so I'm going to talk about that.
Okay.
So, that's a good point. If you were to just FOIL out the denominator, notice how things get a little mixed up. So, this tells us, can we just simply say that x is b and 7 is a? Okay. We can't. It has to be in the correct order. So, remember, up here, it had our number, then our square root. So technically our number is -7, so -7, okay, plus our square root. This right here, the square root of x minus 7, is the same as being written as this. Okay, I just put the number first and then the square root second. Which means that when I write this out and I square it, this is going to be my a and my b. So it's going to become, wait, did I miss something here? That gives me the same. Yes, this is going to give me, because my a is only this 7. This is going to give me -49 plus x. And if I was to rewrite that, that becomes x minus 49. Okay, so when we're labeling our a and our b, we're not including the sign for a, because we're already changing the sign here. If this seems a little confusing, what I would do every time to get the correct answer is just FOIL them out. FOIL them out. If you don't want to follow this formula, don't. Just FOIL these, and you'll get the same thing. And I'm gonna do that for the rest of the problems where I just FOIL. Okay. Honestly, this concept here of the conjugate, you just remember that this is the opposite sign. No one really remembers that this is the formula. Because why remember an additional formula if we could just FOIL? Okay. But I just wanted to introduce it to you. So on number 12, we will, from then on, just FOIL everything once we write the conjugate. Okay. Oops. So continuing on with this problem, can we combine any like terms in the numerator? We have 4 square roots of x and 7 square roots of x, which can become what? (11 square roots of x. Okay, because we have 4 of them and then we have 7 of them, so combine them, we have 11. then we have 28, then we have x. Okay, they don't combine with anything else. And on the bottom, we have that x minus 49. Can anything cancel on the numerator and the denominator? So actually nothing can cancel. Why can't anything cancel?
There's addition and subtraction attached to them.
Good. Because of our operations of addition and subtraction, we can't cancel anything, so this is our answer. I'm just going to write that off to the side. Okay. So think of this as like method 1, method 2. Method 1, we were using that conjugate formula idea. Method 2, the one that I prefer, is just to FOIL everything out. So that's what we're going to do in 12. Okay. So looking at the denominator here, what would be the conjugate of that denominator? Correct. The only thing we change is the sign. So we're going to multiply the top and the bottom by the square root of 2 plus 4 square roots of 5. And since both the top and bottom have 2 terms, we're going to use the FOIL method for both. So starting with the top, we have 3 square roots of 2 times square roots of 2. What is going to happen to those 2 square roots of 2? So the square roots are going to cancel, right? And what number do we have left there? 2. So this is technically 3 times 2. What about 3 square roots of 2 times 4 square roots of 5?
12 square roots of 10.
Correct. So this is plus 4 square roots of 10 because we multiply the outsides, or sorry, not 4, 12. We multiply the outsides, so 3 and 4, and we got 12. Then we multiply the insides, 2 and 5, and got 10. Okay. Now looking at the other part of the FOIL method, so we have 2 square roots of 5 times square roots of 2. So this is going to be 2 square roots of 10. Then we have 2 square roots of 5 times 4 square roots of 5. So multiplying the outsides, 2 times 4 is 8. And then square root of 5 times square root of 5 is going to give us what number? Because they're the same, so they cancel out the radicals. 5. So 8 times 5. Okay. Before we simplify that, let's go ahead and FOIL the bottom. So on the bottom, we have the square root of 2 times the square root of 2. The square roots are going to cancel, and we're going to be left with 2. Then we have the square root of 2 times the square root of 4, or sorry, square root of 2 times 4 square roots of 5. So this is going to become 4 square roots of 10. Then we have negative 4 square roots of 5 times square roots of 2, which is going to be negative 4 square roots of 10. And then lastly, we have negative 4 square roots of 5 times 4 square roots of 5. So multiplying the outsides, negative 4 times 4 is negative 16, and the square root of 5s are the same, so the square roots are going to cancel, and we are left with what number? 5. Okay, so we foiled the top, we foiled the bottom. Now we're looking at just this part off to the side, and we're going to simplify. Okay, so simplifying the numerator, we have 3 times 2, which is 6. We have 12 square roots of 10 and 2 square roots of 10, which can combine to what? 14 square roots of 10. And then we have 8 times 5, 40. So looking at our numerator, this tells us we have 6 plus 40, which is 46, plus 14 square roots of 10. Now we're going to do the same for the denominator. Do you see anything that we can cancel right away? The 2 center terms are going to cancel. And so that means we have this negative 16 times 5. What is that going to give us? Negative 80. So we have 2 minus 80, which is 78. Okay? Correct, negative 78. Okay? Before we say this is the answer, we have to see if we can take out a GCF from the top. Is there a GCF that we can take out of 46 and 14? 2. So that means we would have 23 plus 7 square roots of 10 over negative 78. Can we simplify that 2 and that negative 78? Yes, so that 2 would go away, and the negative 78 divided by 2 is negative 39. So that means we have the answer of 23 plus 7 square roots of 10 all over negative 39. To me, this is a lot simpler than trying to remember that conjugate formula. As long as you remember that for the conjugate, you change the sign, that's all you need to remember. So if it's positive, you change it to a negative. If it's negative, you change it to a positive.